afternoon, welcome. As the scientific coordinator of the Center for Philosophy of Science at the University of Lisbon, it's a high delight to open this session of our permanent seminar, now again on online format. Today's speaker will be Paulo Castro. Paulo is our higher researcher, and since 2019, I believe, has been the assistant head of our research group on philosophy of natural sciences. He's worked mainly in philosophy of quantum mechanics and in philosophy of artificial intelligence. So I just want to thank Paulo for accepting our invitation to do the session, and it is a great pleasure to have you all here at our permanent seminar. Silvia, the floor is yours.
Okay, thank you very much, for having me, and thank you all for coming. So I'm going to share.
Wait for Silvia.
Just once, yeah, I will just say, welcome everyone. Thank you, Paulo, for accepting our invitation. And Paulo will talk for about 40 minutes, and then we will have the Q&A session. I will moderate the questions. We are recording this session. We will record Paulo's presentation, but we will stop recording during the Q&A. So you can feel free to ask all your questions. This is it. Paulo, the floor is yours.
Okay, thank you. So I'm going to share my screen. Okay, and there we go. Do you see it?
Yes.
Okay, all is well then. I'm going to talk about what we call the philosophy of pilot wave theories, and in this talk I wish to deflate three quantum mechanics orthodoxy claims, mainly that the Psi wave has the metaphysical status of a non-physical wave, entailing the role of a probabilistic causal agent, and also with this, along with the reification role of the conscious human agent. I want also to deflate the claim that the complementarity between space-time locality and deterministic dynamic evolution is the only phenomenological case in a quantum type formalism. And finally, I wish to deflate the superposition claim of that potential physical mutual exclusive states is the only argument for interference patterns in particles' behavior, and also explaining the entanglement behavior. This is work that has been done since I think for 7 years or so, and I wish to say thank you to Professor José Roca and Professor Rui Moreira, and also to Professor Mario Gata for all the discussions, guidance, and of course help, which is much needed in this kind of things. Before I tell you what I think is a pilot wave phenomena, let me try and show you what it is with this movie, this video, which was made by Daniel Harris and John Bush from the Department of Mathematics of MIT. And so, it's not working, of course, but why should it be? And okay, I think it will start now. Okay, this is a droplet. What the guys at the MIT are doing is experiments with an oil which is shaken with a vibration, and a little droplet is launched to the bath of oil, and what it does, it creates waves that in turn will alter the movement of the wave, and the wave and the particle will be propelled by its own field. I don't know if you are seeing this quite right, but okay. So what this means is that you have a phenomena in which the droplet is generating a field in the bath, and the waves from the bath are guiding the droplet. And this, I'm going to stop this a bit so I can speak. And so if the thing is, you have a rig. The rig is an oscillating platform, which is being fed with the frequency, and the frequency will, at the top of the surface of the oil, will produce what is called Faraday waves. These are waves that are stationary, and then the droplet will start bouncing on the waves, and then as we reach a certain frequency called the threshold frequency, the droplet will start moving in a particular direction, and then it will reinforce the waves that are on the top of the bath, and the waves that are reinforced will again guide the trajectory of the droplet. And this is of course a part of the video where they have accelerated the thing. So this is a very interesting graphic. I will stop it again so you can see it. This is a graphic that is measuring the position, the sequence of positions of the droplet in a confined area of the box on which the bath, the oil bath, is being delivered to the droplet. And the thing is, as the droplet is moving, it will kind of form this pattern, and it will kind of probabilistically be at points where it will be more at some points than other. And this is kind of thing that reminds the probability distribution. And it's, you see it here, it's an analogy to what could be happening with quantum mechanics. So I'm waiting for the video. Okay, so we are in fact facing a kind of exposed variable theory of pilot wave phenomena. And the physical picture would be this: there's a fast dynamics, a bouncing at resonance creates a monochromatic wave field. There are intermediate pilot wave dynamics. There is droplet rides its kind of wave. This, as the video says, there is a kind of analogy between this kind of phenomena, which is being led in experiments which are macroscopic, and the phenomena in quantum mechanics. So that's why at the MIT they are doing this kind of experiments. They are trying to get analog phenomena which are being studied macroscopically, and there is a kind of correspondence between what is done in the hydrodynamic environment and what could be happening in quantum mechanics. So after I have shown you what is a kind of pilot wave phenomena, let me tell you what I think, or what could be defined as one. First, there is a propagating oscillator, which is the particle. In the case of the droplet, it would be the droplet being actuated by the gravitational field of the Earth, and it will be falling. Then it will interact with the background medium on which a coherent set of primal waves, which we can think that would be elementary oscillators, can be used to compose a wave field. The particle and the wave field then interact in so much that the particle generates and reinforces the wave field, and the last alters the kinematic behavior of the particle in a guiding relation. The wave field encodes information about the set of possible physical behaviors for the particle. This is important in the hydrodynamic case because what they think is happening is that as the droplet is falling on the oil, it will generate a wave, then another wave, and all those waves which are being generated in different times, in different instants of time, will compose a kind of memory, a drag memory of the history of the particle. And that has some kind of influence along the way for the future positions of the particle. John Bush and his colleague Oza have defined the pilot wave phenomena, saying that first the pilot wave must be generated by the particle, then a free particle thus responds only to its own field. Second, there must be a memory of the particle path recorded in the pilot wave field, which renders the particle dynamics in hereditary mode. Third, there must be a resonance between the particle and the wave field, which ensures that the pilot wave field will be quasi-monochromatic. So now that we have seen, well, in short, what is a pilot wave phenomena, let me deal with the first claim from quantum mechanics, which is the psi wave claim, and it can be exposed this way. The psi wave as the metaphysical status of a non-physical wave that entails the role of a probabilistic causal agent acting on the behavior of particles, along with the role of the observer as the conscious agent that collapses the wave and brings material, makes the thing material in the world. Therefore, we cannot measure such wave. So this, of course, comes from the much celebrated double slit experiment, which usually is presented showing which way the particle goes, but I'm going to show you in the kind of wave mode. And you have, as you know, you have a generator, a source which generates electrons or some kind of particles. And as long as we don't know which way the particle goes, there will be an interference pattern after the slits, and this is attributable to a kind of interaction between the two waves that are generated coming from one slit and another. The narrative goes that when I finally place a detector at one of the slits, let's say the upper slit, I will, of course, know which the slit the particle has went. And with this, it will collapse the wave, which is symbolized, represented by that explosion there. And the particles will come into the material world, will reify or something like that, and will behave like baseball balls or bullets. And then you will not have the interference pattern anymore. And of course, this is the now I know guy. If you place the now I know guy at the lower level with the detector D2, you will have pretty much the same thing. So let's call pilot wave to the rescue in double slit experiment and kind of see what could be happening. The picture we are trying to use here is the one in this video. You can see that the wave is actually moving with the particle at the center. I hope well, the video part of this presentation is not going that well, but you see the idea, I think. It does not move. Copenhagen is kind of messing with this well. And the thing is that as the graphic, there were experiments that were done with droplets and with the bath oil in the hydrodynamic scenario, and in the upper corner, what you have is the double slit here, of course, and there's a kind of very minute interference between the wave that passes here and passes on the other slit. And that interference kind of alters the propagation of the particles and make this kind of interference pattern, which is not the same interference pattern as the one we can see in quantum mechanics experiments, but it kind of shows that there is some kind of interference. Probably the problem here is that the slits are too parted away. The distance between the slits is very, very long compared to the wavelength of the wave itself. On the lower diagram, you have no slit, and this is a kind of graphic that would result with no interference pattern. So, oh, now it's kind of moving. Okay, next slide. So what indeed happens to the wave when I place a detector? What is the mystery that we have to solve using pilot wave theory? Well, what indeed may happen is that the relative coherence between the two waves coming from the two slits is highly disturbed. And so as the phase, the coherence phase between the two waves is messed up, you don't have an interference pattern anymore. So perhaps one could say that the pilot wave explanation for the double slit experiment would be that when a which-way measure is done with particle demolition or otherwise, this means with the detector placed and detecting the particle, or not detecting the particle, but used in a way that we can know which way the particle went. When the demolition or otherwise directly on the experimental setup, the phase relation between the interfering waves is altered, and so no interference pattern occurs. The active measure then implies a selection that impacts not on the quantum wave field existence, but on the phase relations between its internal wave components. So this means that the wave field exists at all times with the particle. The thing is that I'm just altering the phase relations between the different components on the wave, and so no interference will be observed. And in fact, there is some experimental evidence for a measurement with both which-way information and an interference pattern that was done by Menzel and Pullman and other colleagues. And in this experiment, you have a UV pump, which is in a certain electromagnetic mode. And after that, you have a nonlinear crystal. And what the nonlinear crystal does is that it generates two photons, let's say photon I, which is called the idler photon, which will be detected by the DI detector, and the photon S, the source photon, which will be sent to this double slit here at the front. And as the two photons are entangled, there is a way to know which way the photon S went, one slit or the other, just observing what the photon E, the idler photon, is doing. And what they have seen is that when they move the detector, the DS detector, away from the slit, they will have an interference pattern. So the very curious thing in this paper is that the authors did not abandon the complementarity principle of Niels Bohr, and they assumed that the source photon, which is the one that will be interacting with the double slit, will go along in a kind of superposition where not an empty wave, a vacuum state will be interfering with a state where the particle is. That is, they kind of invoked second quantization to explain this. I think they are kind of struggling with what seems to be an evidence that one can know which way the particle goes and also have an interference pattern. So let me move on. Now let's talk about the complementarity claim. One can put it in this way: the complementarity between space-time locality and deterministic dynamic evolution is the only phenomenological case in a quantum time formalism. Let's start by the complementarity principle. It says that at the quantum level, the possibility of a space-time coordinate description is complementary to the possibility of a causal dynamic description. That is, you either know where a particle is, or you know what is its momentum and where it's going to be, kind of what's its dynamic state, if you will. And this, of course, has a relation with classical physics. I have called this part the Niels Bohr ontology for quantum objects, an interpretation I give to what I think Bohr was kind of thinking. Well, classical physics at the macroscopic level allows for the description of phenomena involving both space and time coordinates, measurable with, well, all accuracy, well, with sufficient accuracy, and both linear momentum and energy values, giving causal dynamic evolution of the system, what I have just told you. So I can see where the system is and and I can have information about its future evolution. So let's take the Broglie relation to see how this comes about to the famous Heisenberg relations and uncertainty relations. With the Broglie relation, which relates the momentum with the number wave of the wave with its special frequency, you have that linear momentum, which is in fact velocity, gives the information about where the object is going to be, provided there is only one value for the number wave, for the spatial frequency of the wave. On the other hand, spatial frequencies will give you the information about the object's actual position, provided there are an infinite number of them that must be summed, and this is in the Niels Bohr ontology, and the reason is the following. We should use an infinite number of space frequencies to know the quantum position. The reasons I have kind of thought, I wish to present are the following. I think the building blocks in Bohr's ontology are infinite waves. This comes from also from the Fourier Analysis. And what I think is that Bohr sought each quantum wave to represent our state of knowledge about the properties of a quantum object. And consequently, this C wave could be thought as an idealized entity relating to every point in space and time, and hence extending throughout the whole universe. So this would kind of make sense, considering the wave an infinite object, although it is very confusing because the wave is not something that exists, but also is something that exists. It does not exist because it's a metaphysical object, a probability wave, but exists because it kind of interacts with real things that we can experiment with and can observe the behavior. And so, well, this is kind of puzzling. Why, again, the second reason would be that at the time quantum mechanics was worked out, sines and cosines were the easier wave functions with a single value for the spatial frequency with the k, as required by the Broglie relation. And there are infinitely spread functions over the entirety of real numbers, and this would be a perfect mathematical fit for Bohr's ideas. And the third reason is that, according to Fourier Analysis, the only way to make unlimited sines and cosines give you a limited wave region where you can coordinate a quantum object is to sum an infinite number of them. As you can see, you have to build what is called a wave packet. So let us see if there is a kind of alternative to this vision, using infinite waves as the building blocks. Indeed, there is. If you use Morley wavelets, you can again use it to sum an infinite number of them with different values of the wave number. But now the expression that that will result from the same operation that you use to get to the Heisenberg relation gives you a kind of generalized uncertainty relation between the momentum interval and the space interval. And this, I hope you are seeing my mouse pointer. What you have here is that this generalized uncertainty relation will have the Bohr-Heisenberg, the Heisenberg relation as a particular case when the extension of the Morley wave is made very large, as here it will go to infinity, and then the term under the I don't remember raiz quadrada in the formula will disappear, and you will get the Heisenberg uncertainty relation. On the other hand, there's another very interesting result here, and the interesting result is that when you have the sigma, the extension of the wave to be kind of the same proportion as the space interval, you will have that for every space interval, whatever its extension, and in particular being very small, you can also have a very small interval for the momentum. And this can be interpreted as the Newton-Einstein case, that is the case where the momentum will be independent, the values of the momentum, the possible values of the momentum will be independent from the values of that we use to coordinate, from the space values in this case. And so you will have a kind of deterministic picture using the same formula. So this means that we can, in principle, have the same theory describing quantum probabilistic and macroscopic deterministic phenomena. Of course, this depends on our acceptance that these waves all exist at all times. And so this is a kind of consequence of allowing ourselves to think in a realistic way. So a last note about this is that this Morley wavelet expression comes from a non-linear differential equation that indeed has the Schrodinger's equation as a particular case. So this is again, you can see the hydrodynamic quantum analog case at the top of the image. And this is to just say that in pilot wave phenomena, you have finite waves, not infinite waves. That just does not make sense. And in the quantum mechanics case, it shouldn't make sense either. The other case I wish to present you, where there is some kind of macroscopic quantification, is indeed a very familiar one and a surprising one, I should say, which deals with the Titius-Bode relation. The Titius-Bode relation is one in that you can get a formula. Indeed, the formula is written there at the lower right place in the image. You place there a number, an integer number, and as you place 1, you will have the radius of Mercury orbit. As you place 2, you will have the radius of the Venus orbit, and so on, until Pluto appears and messes all this, but nothing is perfect. It will go right until the planet before Pluto, which name I don't remember now, Uranus, perhaps, something like that. So another case of a macroscopic pilot wave model, if you will, a possible pilot wave model. So last claim, the non-locality claim. Superposition of potential physical mutually exclusive states is the only argument for interference patterns in particles behavior and for the entanglement behavior. This is, well, it comes from the belief that we must have entanglement, but also no faster than the speed of light situation. That is, you should have things that can be correlated, instantaneously correlated, but without a faster than light than the speed of light signal going between them. And in fact, in an entanglement situation, the whole wave expression contains all possible behaviors for the entangled particles. And when an observation is made, the two seem to relate closely without communicating to each other through space. And this, I think, evokes a hyperconfiguration space scenario. And let me go back to the configuration space in both classical and quantum mechanics case. And as you know, you can represent a particle that is a system of particles, pretending that it is a kind of n particle which lives in an n-dimensional phase space, as the one here with Q1, Q2, and so on. And then each one of these particles, in fact, is space described as a particle having an x, y, and z coordinate. And so you have a superspace with 3n dimensions. And in classical mechanics, one can say that whatever the function that I'm using to deal with this 3n particle, the function represents the global state of the system for a particular configuration of the n particles. It is thus a description about the particles, and it's a kind of hyper-representation. One accepts that the particles in this case, in statistical mechanics and so on, exist in a 3n configuration space outside the usual two-dimensional space. On the other hand, in the quantum mechanics, one could say, and this is what I call the pilot wave theory, strong nomological interpretation for quantum mechanics, that there is a function, which is the psi function, again, talking about several particles, kind of represented in one, that would represent a physical evolving structure encoding all possible behaviors to be performed by the n particles. It is a description not about the actual particles, but about all their possible behaviors encoded in the memory. And this is my, I think, most ideal metaphor. And what I'm saying here is that the psi wave, it's an evolving memory of all possible positions and momentums for all the particles that are inside the wave. It's kind of an holographic representation of information. I think when I was younger, I read much about the holographic principle, and I kind of it's influencing somehow now. But the thing is, with this, let me go to the next. One can say that in the classical mechanics, the function, the configuration space function, corresponds to an abstract description without any direct physicality of its own. That is, one cannot prepare an experiment that will change the overall energy of the systems prior to altering the individual energies of the particles. But in quantum mechanics, with this strong nomological interpretation, one could say that the psi wave, the wave vector function, corresponds to a physical structure with undulatory characteristics that can be acted upon. One can prepare an experiment that gives rise to interference patterns prior to altering the individual cinematic states of the particles. And however, the problem will remain that the dynamic evolution of this wave must still be described in a multidimensional space, which seems to elude again the physicality claim about the psi wave. Well, using position as an example, since the multidimensional data, which is 3n, now refers not to the actual positions of the n particles, but instead to all possible positions that each and every particle can assume, I will suggest the following hypothesis. And it is this. I call it the encoding compression hypothesis, and in the strong nomological interpretation, and the hypothesis goes like this. The dynamical evolution description of the psi wave in a 3n dimensional space strictly refers to the nomological information encoded in the physical wave and only coincides with the three-dimensional wave dynamics for the case where you have one particle. That is, all multidimensional nomological information is encoded in a compressed way in a 3D wave structure. So what I'm saying here is that the quantum mechanics calculus is a calculus about information, dynamics, processing, encoded in a three-dimensional wave. That's my suggestion. This invokes what can be called, again, calling for the generalized uncertainty relations. This can be kind of conceptually crossed what I have called memory densities for space and time values. You see that you can consider that the sigma x, which is the sigma for the spatial extension of a wavelet, is a kind of spatial memory range. So in this case, let me read, it's easier for me. Delta x and delta t are the intervals of possible values for x space and t time values nomologically related, that is, that can occur for the same physical phenomena, while sigma x and sigma t represent memory ranges of the carrier wavelets for all possible values of x and t that can be encoded in the wavelets. And then using the relations, the generalized uncertainty relations, we will get the relations between what I can indeed measure as space possible values and momentum possible values, as well as time possible values and energy possible values. And those will kind of depend on the memory density of the information encoded nomologically in the waves. So I'm kind of using a metaphor where the waves are part of let's say, a supercomputer, which would be a metaphor of the time. And I'm saying that the physical phenomena is something that depends on some kind of memory that encodes the possible information, the possible behaviors that things can have. So, using the same nomological framework now to explain entanglement, it so happens that this uncertainty relations, this generalized uncertainty relations, are to be thought about as representations of something that exists. And so I can kind of use both and combine them in an algebraic way and get from there what can be called generic space-time relation. Well, this generics, never mind the strange form of the relation. What is important to see here is that you have here that the space delta x is proportional to time as it should be. This just means that to cross an extension of space, I should have to do it in a certain time, and this certain time, should I go in a kind of average way, this time is proportional to the space which has been crossed. But things can be more strange than that. You can have something, because if you are using a metaphor where you have nomological information informing the way things can happen, of course, you can kind of have something stranger programmed, stored in the memory of the encoding wave. So you can have something like this. And this is the point made here when we mess with the memory ranges for space and time. If you make those both very large, if they tend to infinite, the formula will get again the linear case. That is, space which I have crossed is proportional to the time I have used to cross it. But another way to get this would be to have a proportional relation between the two memory ranges for space values and for time values. In the second situation, which I have called the entanglement situation, if you tweak around with the memory range for space and you make it very large, and if you make the time memory for the time the memory for possible values of time encoded in the wave to be well, very near the actual times that are being used by the system to perform, to behave, then you will get the following result. Whatever the time used, you will have a very large distance crossed. So in this kind of situation, you can use the following interpretation. There is a kind of case using the relation between memories and the kind of setup of the nomological memories, where you can have a very fast moving sign between one particle and the other that are correlated. Of course, this would mean that you would have something faster than the speed of light happening, but well, in fact, in the tunnel effect, you have something that can be seen like that, but that's another story. So to finally wrap it up, because it's hard stuff here, we can think about a putative future pilot wave gravity, and that would go something like this. What is space-time? If I think, if I consider that the waves are encoding all possible behaviors of the particles inside them, then I can kind of think that space-time region is the set of all possible space-time coordinating and dynamical values characterizing any interaction within the subquantum wave. And this would be kind of equating the subquantum waves to space-time itself. And so at the most primal level, space-time will be characterized by a nonlinear relation between space interval and the time interval using the generalized space-time interval. And this would combine eventually with other equations would allow me to get entanglement, tunneling. We have also a solution for tunneling using this, and well, general relativity phenomena, but I'm kind of dreaming at this point, and so I must stop and get myself ready to be asked for something about all this. So I thank you very much, and this is the end.